is 2.88. Number 27, yes. All right, so we've got a compound interest situation related to continuous compounding, and we want to know the doubling time. Now, this problem is worded just a little bit weirdly. Over here, they say continuous compounding. Right, so we're always collecting interest. But over here, they say they gave us an annual percentage rate. Okay, so an annual percentage rate is not the same thing as an exponential growth rate or a continuous growth rate. So those are two different things. So an annual percentage rate means that you get that growth multiplier. So what do they give me? 8% here. So my growth multiplier based on that would be just 1 plus 8%, right? So 1.08 is the growth multiplier. If I wanted to turn this into that P e to the RT formula, then what I would have to do is I would have to set e to the r equal to 1.08 to figure out what the continuous growth rate is. Okay? So there's a difference between annual growth rates and continuous growth rates. Now, I actually don't even need the continuous growth rate to solve this problem, it turns out. So I'm going to shortcut that. Okay. So this step right here is optional for this problem. So instead of writing the formula as F equals P times e to the RT, I'm just going to write it as P times 1.08 to the T. And guess what T is measured in?
Years.
Years, because it says annual up there. Yeah. Yeah. So the trick on this problem is to realize they gave me an APR, not the exponential growth rate, which I need for e to the RT. Okay. You can find it if you want, but it's not necessary. Next thing to consider is it really doesn't matter that I'm starting at 72,000. And I'll show you why, because they want me to find the doubling time. So new page. More fully, my formula would be 72,000 times 1.08 to the power t. That is a continuous formula because t is a continuous variable. Let's see, if I want to figure out at what time it doubles, I have to find the amount of the double. Well, if I started at 72,000, double that would be what, 14,400? So that gives me 72,000 times 1.08. T equals 14,400, right? You agree that's double what I started with? Mm-hmm. Okay, what would I do to solve this?
Divide by 7.
Divide by 72,000. What's 14,400 divided by 72,000? Tyler, 2. So I get 1.08 to the T equals 2. So the bottom line is whenever you're looking at W time, doubling time, it doesn't matter what you started at because you divide that out. And you just want to know for what time your base is going to give you a 2. So it doesn't matter whether you started at 50,000 or 5,000 or $2. Same doubling time. Doubling time is only based on the rate. That's it. So then to solve this, I would just take the natural log of each side. So if I take the natural log of 1.08t, I have to also take the natural log of 2. Logarithms have this wonderful property that you can pull the variable out. So I got part of it. If the variable is, power. You can pull the power out as a constant multiple. Divide by the natural log, and then I get the doubling time here. T is the natural log of 2 divided by the natural log of that base. And so whatever that comes out to be, that's the doubling time. Is it close to the doubling time if you just let the exponential growth rate be 8? Yeah, it's close, but not close enough. So I got a few homework questions from people about this, saying, I let e to the r, that r be 0.08. Why didn't that work? And this is why. Okay. And again, almost every problem in this section actually didn't involve calculus, but coming up with a formula like this, to know that's the kind of formula that involves calculus, because it's about derivatives. All right, Ms. Miller, you said you had a homework question. Do you remember what it is? 2.9, number 13. All right, let's go back. And so you're ahead. Wow, congratulations.
And that was the first.
Number 9, you said?
13.
13. All right, Rob. 13 says, okay, I'm almost ready to do that. So give me 1 second, then I'll do that problem. So I got to go back. What's that?
Vitor just texted me and said they can't find the video link.
You can't. I thought I posted it. Sorry, Vitor. It will be there in 1 second. Calc 2 live on Friday. Post. All right. Okay, so I got to finish up what I started, ended with last class, and then I'll do this problem here. So last class, we used the idea of an inverse function to figure out what the formula was for the arc hyperbolic sine, or the arc sinh, and I got this funky logarithmic function here. So the next thing I want to do is show that the derivative of that funky logarithmic function is this rational function over here. So let me go through that, and then we'll apply it, look up some other formulas. So I'm going to rewrite all of that. So arc hyperbolic functions are logarithms Yay, Vitor. Sorry, I forgot to post the link, Vitor. And yet last class I showed that the arc sinh of x is equal to the natural log of x plus the square root of x squared plus 1. So next I'm going to take its derivative, clean it up a little bit algebraically, and then we'll just look up the other formulas we need. So I want to know what is the derivative with respect to x of the arc sinh. Which means I need to take the derivative of this logarithmic function. Oops, I missed something there, like the logarithm. Right. There, spider. Thank you. Okay, so derivative chain rule. I got a function within a function within a function. Okay, so this is going to be a bit of fun. Let's see. What's the derivative? What's the outer function?
ln.
ln. Okay, so derivative of ln is just 1 over. So to start off with, I'm going to get a 1 over x plus the square root of x squared plus 1. Chain rule says multiply that by the derivative of the inner. The inner is x plus the square root. So parentheses, what's the derivative of x? 1. And does anybody remember the derivative of a square root?
X.
You could rewrite it as x to the 1/2. Right? Or you might remember that it's 1 over twice the square root. So I'm going to go with that version. Now, was it just a simple square root of x there? No. So the chain rule says you have to multiply this guy, just the 1 over that twice the square root, by its derivative of the inside. What's the derivative of x squared plus 1? 2x. Yeah, so the 2x just goes there. It does not apply to this 1 over here. It's only times this fraction. Okay, I'm done. Now I gotta clean all that up. Okay, so cleaning that up, first I'll do just a little work here, then I'll rewrite it. This 2 here divides with that 2 right there. And then otherwise, I'm just going to take this parentheses and slap it in the numerator. Okay. So now I have new page, blue, fraction. In the bottom, we have x plus the square root of x squared plus 1. In the top, we have 1 plus x over the square root of x squared plus 1. So we have a couple of options here. This is a complex fraction. One routine for simplifying complex fractions is to perform the addition in the numerator by finding a common denominator. The other way is to multiply top and bottom by the common denominator. Anybody want to suggest a strategy?
What was the first one you said?
You could clean up the top by finding a common denominator, or you could multiply top and bottom by the common denominator. Okay, multiply top and bottom. So then the common denominator here, well, there's only really one denominator. It's the square root of x squared plus 1. So I have to multiply that there and down here. I'm going to do that selectively. I'm going to leave the big denominator in factored form. So I'm going to leave it as x plus the square root of x squared plus 1 times the square root of x squared plus 1. And you'll see why in just a sec. Then I have to distribute this red one to that and to the 1. When I distribute it to this fraction up on the top, well, they cancel, mostly, and I'm left with just an x. When I distribute to the 1, I get the square root of x squared plus 1. Why is that lovely?
Oh, that's a tough one.
Because that is the same factor that appears in the bottom. So what's a thing divided by itself? 1. So this simplifies to be 1 over the square root of x squared plus 1. Eek. Not too bad. It took a page or so. So yesterday it took me like at least 10 minutes to come up with a logarithmic formula for the arc cinch. It takes about the same amount of time to come up with a formula with the arc coach or the arc tangent, and it takes about this much work to find the derivatives of each of those. Okay. So I'm not going to find all of those. I showed how it's the same technique for all of them pretty much. It's just a matter of grunting through it. So I'm just going to go to a page that shows them. And that's something we probably want on our notes. Anybody already add those to the notes?
What?
You added some? Yeah. So the notes, remember the notes page is going to close today. Whatever you guys put in there is what you get for the test. All I'm going to do after you're done putting stuff in there is I'm just going to clean it up a little bit and print it.
I'm putting half-life and compound interest.
You can put in half-life and compound interest if you want. Yeah, so you guys need to police it yourselves, and I'm just going to go in and make it pretty.
After amount after.
So if you think there's something missing, get it in there before midnight tonight. What's that? You're not going to have to derive any of these. You're just going to use them. Yeah. So I did the hard part for this one. Otherwise, we're just going to use the formulas. And the formulas you can find either in our book or you can look them up and like Wikipedia has them or lots of sites. Kyler, did you have a question?
I put those on the.
You added those in there?
Yeah, I think
Yeah.
so.
Way to go.
Yeah, no, you did.
So other things I'll do is if there's a slight error in anything, I'll clean that up. I'll just make the whole thing prettier and more organized. Okay, so let's go to Miss Miller's question. She wants to know what's the derivative of x to the 4th times the arc cinch of 3x. So let's do it. Let me copy that into a new page. So remember that little -1 there just means the arc function, the inverse function. And different math people have different preferences. So somebody else wrote this problem. I prefer the arc notation. Anyway, what we just established is that the derivative with respect to x of the inverse hyperbolic sine of, I'm going to put a u in there for fun, is equal to u prime over the square root of u squared plus 1. Right, so I'm throwing the chain rule into that version of the formula. So that's the chain rule version of the formula. So here, not only do we have to apply that formula, but we also have the product rule going on. So let's see, f prime, product rule gets to start this out. Derivative of x to the 4th, 4x cubed. Product rule says leave the next function alone for the moment. So that's the hyperbolic sine inverse of 3x. Then the chain rule says add on to that, leave the first function alone. So that would be just x to the 4th. And then multiply by the derivative of the second function. Let's see, what is my u here? It's 3x. Derivative of 3x is 3. So there's going to be a 3 in the numerator here. Otherwise, I just divide by the square root of 3x in parentheses squared and add 1. This really doesn't clean up much. The best I can do is factor out an x cubed maybe, but that doesn't really make my life better, so that's the answer. So in this case, I just have to apply the product rule and the chain rule version of the derivative of the arc sinh. The inverse hyperbolic sine. Do you get how I did that? Does that make sense? Okay. Since we are, I think I did everything else I wanted to do in that section. So again, formulas for these things exist in the book. And I heard Kyler added some of those formulas, maybe all of them, to our cheat sheet. So here's the derivatives of the hyperbolic, the regular hyperbolic trig functions and corresponding intervals.
Is hyperbolic secant just sech?
Sech, yes. And maybe this one's catch. I can't remember how it's pronounced.
And koth.
Koth. I think it's koth. I think you're right. Yeah, and so here are those derivatives right here. We found this one. Blow that up a touch. The hyperbolic cosine is got a minus in there. Doesn't that look like another function we found a derivative of before? Which one does that look like?
The arc sine.
Arc sine, but arc sine is 1 minus. And it turns out changing the direction of that is a big deal. It is a big deal, right? It's a totally different function. Okay. They look pretty similar. How about, this looks familiar, 1 minus x squared in the denominator. What's that look like?
1 over 1.
The arctan is 1 over 1 plus x squared.
Yes.
Changing it to a minus is a big deal. You end up, because what is a hyperbolic inverse function? It's just a logarithmic function. That's all it is. We just gave it a fancy name, but it's just a logarithmic function. Okay. So it turns out if you change the plus to a minus, you move from having arctangent be the antiderivative to a logarithmic function being the antiderivative, which makes me wonder, there must be some physical connection between exponentials and logs and sines and cosines, right? Because these are too close to be, yeah, and it turns out it's more than just the unit circle and the unit hyperbola. There's more to it than that. And for those of you who take Calc 3, you'll see that relationship there.
For our knowledge to this point, the relationship between sine and cosine is Pythagorean, right?
Yes, but now what I'm saying is because the formula here of the derivative of the arc hyperbolic tangent, which is basically the derivative of a logarithmic function, looks so much like the derivative of the arc tangent, there must be a connection between regular trig functions and exponentials and logarithms. And it turns out there is a very interesting mathematical connection to them. And I'll give you a hint. It's I. The imaginary number connects them.
Of course it is.
It's nuts. Yeah, I couldn't believe it when I learned that years ago. And every time I stop to think about it, it's like, how is this
I know I
possible?
saw an eye on that wiki page.
Yeah, you probably did in the wiki page. They probably go over it. All right, let's do some other problems. I found that in the section 2.9 homework, there was a very interesting revolution problem at the end.
Oh, this one doesn't use the title of Q.
Yeah. Okay, there's this cooling tower for a nuclear power plant that's got this pinched chimney shape. Like we've all seen pictures of those. The function this kind of sort of looks like it, but laying sideways. Let's hope no power plant ever lays sideways in our lifetimes. So I'm going to take a graph, look at a graph of that, and see if we can figure out what do we want to try to. We want to rotate this about the x-axis.
Yeah.
All right, so let's graph that sucker. Let's see, 60 and 67,600. Oh, this is going to be an interesting graph.
Which number was this?
This is the last one,
16.
number 16. All right, so f of x equals 60 times the SQRT of 1 plus x squared divided by, 67,600, which I believe the comment was given. And they said to look at this between negative 190 and positive 260. Okay. So back here, enter, and then I just need to change my scale. So I need to get over to negative 190 and positive 260. And if you're using Desmos, you can go type those in. All right, that should be enough. Now I just need to drag it down till I see it. Ah, there it is. Okay, so now I'm going to draw in my boundaries. X equals negative 190. X equals positive 260. Okay, so that's my the edge of my cooling tower laying on its side. We're going to revolve that around the axis. So let's see, the height over there is around 85-ish. The height over here is around 75-ish. All right, so let me make a rough sketch of that. So f of x equals 60 times the square root of 1 plus x squared over 67,600 looks kind of like this. Right, not too bad.
Is that, it's laying on its side, is that only half of the tower then?
Well, so I got to revolve it to make the tower.
Oh, okay.
Yeah, so this just gives me the outline of the tower. I was told to revolve it around the x-axis. And so remember, on the test, I want detailed drawings of what your picture is to help you set it up. All right, so we need to make a decision. Do we want to use discs or shells for this? Now, what's the difference? Discs are washers, perpendicular rectangle. Shells have a parallel rectangle. So I kind of draw each in and get a feel for it. So washers are discs, that's my rectangle. And that rectangle needs to slide that direction and that direction. That looks pretty cool. I like that. One sec, William. If I was going to do washers, then washers would have to go this direction, which means I need to draw in these boundaries, which means sometimes I'm just between those boundaries, but other times I'm between the boundary and the curve and the boundary and the curve. Eek, messy, do not like that. Not gonna do washers here. I mean, shells. I'm gonna do disc/washers. William, your comment?
I was gonna suggest that doing the disc method.
Is the way to go,
Shell.
yeah. And for me, like if I draw the first picture and it looks good, go for it. But I usually kind of sketch them both out to get an idea so I don't waste my time. So it's usually worth my time to do that. So let me get rid of those extra lines. Okay. All right, so other things I need to put in here to get this right. I'm gonna draw in my boundaries on the side. If I'm going to use discs, I'm going to make a note to myself that I'm using discs. And this particular disc has a dx, so I'm integrating with respect to x. So this must be my a, the negative 190, and this must be my b, the 260. Formula for discs is just pi times r squared. Since there's only one relevant curve here, I don't have a big R and a little r. And my R is that top up there. So my R is just this function. So that means I just need pi times f of x squared. And I'm going to integrate that from negative 190 to 260. Okay. So in my picture, I drew the curve, I drew the boundaries, I drew my little rectangle, I labeled my dx to confirm to myself I'm integrating with respect to x, not y. And I want to confirm to myself that I have a single radius the whole way. To do that, I have to imagine sliding that rectangle left and right, right? And the top is always just that curve, right? And the bottom is always just the axis. Okay? So I can't get it right unless I can confirm all those things to myself. Squaring this is nice. That gets rid of the square root, right? That's even more delightful. And I'll have the square of 60 also. So then cleaning this up a touch, I'm going to pull the pi out. I'm just going to call it 60 squared, right? Because I have to square f of x here. And then otherwise, if I square that, that gets rid of the root. So now I just have 1 plus x squared over 67,600 dx from negative 190 to 260. So pulling out the constants is part of me cleaning up to make sure the antiderivative is easy to take. Would you agree there's really not much else I can do to clean this up algebraically?
Yeah.
No. Yeah.
Yeah, there's nothing much I can do there. I don't want to bother finding a common denominator. I don't think that makes my life better, but you could always try that. Okay, so I think I'm ready to just take an antiderivative. Okay, so new page, let's try that. So I currently have, not pen. I currently have pi times 60 squared hanging out front. What's the antiderivative of 1? X plus, now dividing by 67,600, that's just dividing by a constant. It's like multiplying by a constant. It's just hanging out. So that's just sitting there, 67,600. Sometimes I just write it as 1 over pulled out to the side. And then what's the derivative of x squared?
2x cubed. Or 3.
One
Oh, 1/3 x.
1/3 x cubed or x cubed over 3. Yeah. So I'm going to write it as times x cubed over 3. And now I just have to evaluate that, bless you, from negative 190 to 260. And in this case, I think I'm ready to just say GeoGebra or Desmos, my function is this. Do the evaluation, then multiply by pi times 60 squared. So that's the easier part. I'm going to let you guys finish that some other time, but it's the setup that is the important part. And I can't emphasize enough drawing the pictures. And on the exam, both the take home and the in-class part, for any problem that involves generating a volume or that involves, say, work, I expect some kind of picture to go with it. And I'll remind you that on the test. Okay, what else should we do? It's review time. Should we do a work problem maybe,
What did we do at the
or
beginning?
what's that?
What did we do at the beginning?
In the beginning, we just did area between two curves, was where we started.
Just do it.
Should we look at one of those? Okay. So, let's see.
Oh.
So there's plenty of practice problems. So you could go back and review your homework if you want. The homeworks are all in review mode and accessible. The take home here isn't quite accessible to you yet. I have it password protected at the moment because I'm not done editing the questions. But as soon as I'm done editing, I'll remove the password and you'll be able to get into it. So I've got the practice exam I posted. Let me pop that up. And then there's a ton of practice problems here that you could jump into. Let's see what I put on the sample. So on the sample, I said, hey, here's a bunch of functions. Can you find me an antiderivative? Okay. Some of them involve substitutions. Others you can just kind of look at and do. Others you would have a cheat sheet to look up. Like, would you expect to find each of these last three on the cheat sheet?
Yeah.
Yeah. This one right here, anybody recall? Square root of
Since-
1 minus?
No, coach.
Arcs.
Arch. Coach.
That's the sign.
This would be arcsine.
Oh,
Oh,
who's
this is
1
arc
minus
sine.
x minus
Yeah.
1.
If
it's
Underneath, that's
X
coach.
squared minus
Arc
1. This one right here would be the arc cosh.
That's
And how about this one down here?
Arcs.
This is arcsinge down here. Yeah. Okay.
Good thing we
You
got
look
that cheat
good.
sheet. Oh, hey, maybe we should put the derivative of the arc sine or cosine tangent in there.
That would be a good idea.
Did
Yes.
we not have those already?
Nope.
I don't know if anyone put them in yet. Yeah,
Thank
so
you.
that'd be a good
Exciting
thing. Yeah. So if you
stuff.
think of any integral formulas we've talked about and they're not in that cheat sheet, we'll put them in there.
Yeah, I really do.
You can have anything you want in there.
I did the hyperbolic.
So this wiki page is going to possibly be more than one page.
Oh yeah, it's definitely gonna be more. Yeah, there's no way this is gonna print on one page. Yeah.
I was just curious.
Yeah, it's called a wiki page because it's a web page, but the print version will definitely be more than one page. Yeah. So-
I added like
So this is my, like,
formulas.
I'm giving you guys notes for the test. It's a group notes instead of an individual set of notes.
It's like a flashcard except for 2 pages.
It's a
Watch,
giant
we're gonna miss
flashcard,
one
yeah.
thing. It's gonna
Okay,
screw
so let's
us over,
see.
I
I've
swear.
got the area between two parabolas here, area between a parabola and a line, area between a bunch of different functions.
Is there one that's like a triangle?
So, oh, notice this, the first three areas say enclosed area. So that means those things must define a region that's enclosed. But the last one says total area. Ooh,
Let's do the total.
let's take a look at that one. How is that one different? Okay,
Oh,
so each of these enclosed areas definitely defines a closed region. Okay. This last one does not. Yeah, so we have to consider things might shift who's on top. All right, so we want to graph the sine of x, the cosine of x, and we're going to go from 0 to 5 pi over 4. So whip out your graphing thingy. Start I haven't used Desmos in a while. Let's try Desmos today. All right, so I want to see the sine of x. Let's see the cosine of x. And then I'm going from x equals, so that's the y-axis, that's okay. And then the other one is 5 pi over 4, I believe. 5 pi over 4. Okay. Ooh, that's where the sine and the cosine meet. So that's a convenience. Okay. But otherwise, I have a slight problem because at first the cosine's above the sine, but then later the sine's above the cosine. So that's why I said total area, because if you try to do this in a single integral, some of this area will cancel some of that area. Okay. So that means because it says total area, I have to do two separate integrals splitting on their intersection. Okay. Where do sine and cosine meet? Well, sine and cosine meet, think about the unit circle. For what angle do sine and cosine have the same value? Pi over 4 is one of them. So new page. So just quick trig review here. Consider the unit circle,
Can we be the
right?
user?
On the unit circle,
If we make.
the x value is the cosine of the angle, where that's the angle right there. And the y value is the sine. Remember that from trig way back when? The days when math was a little easier? Imagine that math got harder than trig.
Trig was easy.
Yeah. So I want to know when the sine and cosine are equal. Well, that means I'm looking at the line y equals x. The line y equals x makes what angle with the x-axis? 45 degrees, or, because we don't use degrees in calculus, we use radians, pi over 4. All right, so that's pi over 4, that angle. I need to know what this angle down there is. Well, this is 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. This one is 5 pi over 4, which was the other boundary I gave you anyway. Okay. 5 pi over 4. So fun trig review. All right. So because of the intersection at that angle and at this angle, we need to break it up. So we're going to have one integral from 0 to pi over 4. And then we're going to have, add on to that, another integral from pi over 4 to 5 pi over 4. And in the first interval, if we look at the graph go, the cosine is on top, right? So in that first integral, I would want to have the cosine of x minus the sine of x. And guess what we're going to have in the other interval?
Sine of x minus.
Flip it. Yeah, it's just the sine of x minus the cosine of x. Okay. And so I'm just going to add another side sketch to this. Here is my cosine function. Here is my sine function. And they meet at pi over 4, and again here at 5 pi over 4. Right? And so this is why I have to break it into two intervals. Otherwise, I'll get some negation if I try to do it in one interval. And like I said, the setup's the hardest part. So you're going to first integrate there, and then after that, we integrate out here. And then we just add up those two results. Is finding an antiderivative here hard? Nah, the antiderivatives here are easy. Be careful of your SIGNs, right? So let's just do a little more work just for fun. What's the, I can squeeze it underneath, I think. What's the antiderivative of the cosine?
Negative sine.
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 Was it sine or negative sine? Here's how I tell.
Mine's negative
What's the
sine.
derivative of the sine?
Cosine.
Cosine, so I don't have to switch the SIGN. Okay. Minus antiderivative for the sine
Negative.
is the negative cosine. Double check. What's the derivative of the cosine? Negative sine. So I have to ask myself those questions to get it right. Otherwise, I screw up the SIGNs.
That's the thing, I switched the derivatives and the
Okay.
antiderivatives.
Yeah.
Okay, so that's the antiderivative there. Evaluate from 0 to pi over 4. Okay. Just because I have a zero boundary, is it safe that all that stuff is going to be zeros? No, it's not safe to assume that. It's not always true. Plus, antiderivative for the sine is negative cosine. Antiderivative for the cosine.
Sine.
And there's already a minus there, so be super careful. Integrate that from pi over 4 to 5 pi over 4. So then start plugging in, cleaning up. Turns out this answer you can write exactly. If you plug this straight into Desmos or GeoGebra, guess what it's going to do? It's going to give you a decimal version. Yeah. Actually, let's just finish this one.
But you could just
Write down what you think the answer is exactly, your decimals.
Yes.
Let's see. So a note on the sign of pi over 4. At pi over 4, they're both the square root of 2 over 2. But at 5 pi over 4, they're both negative square root of 2 over 2. And so we have opposites of negatives going on here. So if I go back here, this says what's the opposite of the sign of 5 pi over 4? Normally the sign of 5 pi over 4 is negative square root of 2 over 2.
Mhm.
But I want the opposite of that. So it's a positive. Same thing there. Next, the last line has minus a bunch of negatives. So it looks like I got a whole ton of square root of 2 over 2's added up. Let's see, did I get that right? Ooh, I have a sign error. This is supposed to be a minus, and that's supposed to be a minus.
Can you go back a page?
Oh no, it's minus a minus, it's a plus, I had it right. Ah, darn it. Okay, plus. That's a plus, all right. So we get the square root of 2 over 2 plus the square root of 2 over 2, which is just square root of 2. All right, so let's clean this up. So first pair gives me square root of 2. Then I'm going to have minus 0 plus 1. There's going to be a minus 1. Then I've got plus, these guys turn positive, so I get a plus another square root of 2. And then over here, these minuses minus each other out. So I got more pluses, so I have yet another square root of 2. How many square roots of 2 do I have? 3 square roots of 2, then minus 1. How can I check to see if that's right? Just plug it into Desmos or GeoGebra, and it'll give you a decimal version of this. Fun with trig.
Where do you get the negative one?
Cosine of 0 is 1, but I'm subtracting.
Oh,
So that's-
so you actually missed it.
Is there lots of room for me to mess this up?
Yes.
Yes, so I'm going to go to Desmos next, and I'm going to type it in, and then I'm going to type that in and say, do the decimals match? If they don't, I've got a sign error in here somewhere then. Okay. Do I believe that's the right answer? I'm 91% certain that's the right answer. I think I got my SIGMs right, but I don't know until I check.
I was looking at it. So.
You were looking at, yeah, and that's, maybe somebody wants to throw the unit circle on the cheat sheet.
Can we
That's
literally
what
just
I
put an image
said.
of the unit circle?
What?
Can we literally just put an image of the unit circle on this?
Yeah, you can put images on there.
Okay, cool.
Quick question.
Yes, William?
When the place where you plugged in 5 pi over 4,
Students
wouldn't
take
it be like, negative cosine something, minus sign or something?
The sign of 5 pi over 4 is negative square root of 2 over 2. And I'm taking the opposite of that.
You were taking the antiderivatives of something.
Well, I have the antiderivatives back here.
Oh. Okay.
Yeah, so first I found the antiderivatives, the next page I'm plugging my endpoints in. That's what happened there. All right, we're out of time for fun with math. Take a look at that sample test I posted. It's like a third the length of the practice problems. If you have any questions on those, post the questions to the forum, I'll give one of you guys like 12 hours to respond. If you don't respond, then I'll throw my answer in. If you have any homework or sample problem questions, message me. And if I think it's a good question, I'll post it in the forum for everybody else.
Pirate joke.
And then, oh, the pirate joke. Oh, yes.
Yes.
Okay, let me stop the recording here. Sorry, Vitor, you don't get to hear it.
I don't know if it's-